Hello all. Today I will be presenting on the topic known as sentiment analysis using BERT. We will be using the movie data set where consumer has put down their reviews on each of the movies, and based on the reviews we will be identifying the sentiment for that particular movies. So, so agenda for today's presentation is we'll be understanding what is sentiment analysis, what is BERT, why BERT is required, BERT architecture, explain the encoder architecture. Then we'll go through a code that will have the entire working of BERT. And of course, there are a few of the references that which I have gathered and I have worked with. So, what is sentiment analysis? So, sentimental analysis is a branch of natural language processing that focuses on extracting and classifying the opinions or emotion expressed in text. So, here what I mean is you might have you might have bought a multiple things or multiple products from the Amazon, and each of the product has a review, right? So before buying any product, every one of us goes and check what is the review for that particular product, and based on the reviews we buy the product. Similarly, for every of the movies, whatever the movies you are seeing on the Netflix or maybe any of the OTT platform, we of course see the review of that movie, right? And what are the contents of the movie, and based on that we choose that movie um, to watch and invest our time, I would say. So, so each of the movies or each of the product has the sentiments like positive, negative, or it can be a neutral sentiments as well. And based on that, we make certain decision whether to utilize that particular product or whether to invest in that product, right? So sentiment analysis is additional attribute to each of the object or product given by the consumer, and it is helpful for decision making for in a lot of areas like improving the quality or improving the cost or making some business decision to end organizations. So what is BERT? So BERT is a bidirectional encoder representation from the transformer, is a state-of-art natural language processing model developed by Google. It was trained on the Wikipedia, a huge data set, and it uses the transformer architecture and is been designed in a bidirectional operation. That means it is able to read the context of the sentence from both the direction, from right to left and left to right. So, for example, right, cat eats dash and drinks dash. This is one of the sentence, right? And if I present this particular sentence to BERT, what BERT is going to do is whatever the missing words are there, it will try to understand the context prior to those words, right, as well as next to that word. So here, cat eats dash and drinks dash. So it will try to identify the words, and based on the highest probability of that word will get replaced here. So here there are more chances that cat eats the cheese and drinks the milk can be the most appropriate words that can get replaced. So basically, bird moves into both the direction from left to right and right to left. Similarly, the application for the BERT is it's been used for the test classification like sentiment analysis and spam detection, name entity recognition, so identifying the entities like names, date, and location. It is also used for question answering, so you can ask a question to BERT and BERT can give the answers to you. And also it can be used for language translations. So why BERT is required? So prior to prior to BERT, there were two, or you can say many models that were designed, and the best example is RNN and LSTM. So the problem with those models were it was a unidirection, so that it can only read from left to right or or right to left in the context. Uh, so the impact of those models was, in case if the sentences are too long, it was very easy to lose the context of that particular sentence. right? Let me give an example. John likes to eat pizza, and he also likes to drink Coke. So if the sentence has been presented to RNN or LSTM, it was very easy that LSTM and RNN may lose the context. Like for example, the he part would not be able to understand that the he is the same person or the John is the same person. That should be replaced with the word he. So that was one of the problem that the LSTM or RNN was having, which was been overcome by the BERT. So BERT was developed on the paper known as Attention All You Need. Based on this paper, the BERT was been developed and it uses the transformer architecture. So I'll be taking you a transformer architecture very soon in my upcoming slides. Second part was handling the complex language structure. So the BERT was capable enough to identify the mask language modeling. So all the words which are not present, it was able to identify the missing words you can say, right? And it understand the context and or the context of their particular sentence to identify those words. So let's move to the BERT architecture. So in the BERT architecture, initially whenever the sentences were given to the BERT, right, we need to do a pre-processing of those sentences where we clean the not required non-required characters, or maybe we also need to remove some of the words known as the stop words which are not required to be given to BERT and reduce uh, reduce overwhelming the models by removing all these non-required characters. So the first layer is to pre-process the text and tokenize those text, right? For example, here we have tokenized text from W1 to W5. So those are words that have been tokenized and that has been given to an embedding layer. So embedding layer is responsible for converting the words into numbers. So neural networks understand only the numbers, and the embedding layer has a responsibility converting those into to the numbers. Then the words are being given or the numbers are being given to a transformer encoder. I'll be going in this particular architecture in details on my next slide. The output of this transformer encoder is been given to a softmax layer. The softmax layer is responsible, again, it's again a neural network layer that way is responsible for assigning the probabilities or identifying the probability of the words, which is the outcome of this BERT architecture. So similarly, the sentence that we saw in the last example, cat drinks dash and eats dash. If this particular sentence has been given to this architecture, the missing word can be identified by the softmax layer. With the highest probability will be assigned, this word with the highest probability will be assigned to the sentence. So as we have seen in the previous slide regarding the encoder or the transformer encoder, let me explain you what is this architecture is. So for example, there is a sentence, pizza is awesome. And also there is a sentence, pizza is great. So that is going to get tokenized and that has been passed to the first layer of the encoder, that is word embedding. So the work of word embedding is again converting the words into numbers because neural networks only understand the numbers. And another is based on the number of activation function, it will assign weights to that particular number, to that particular word. For example, if we take a word pizza, the pizza will be assigned an weight, say suppose 7, right? And based on the activation function. So if there are two activation functions, so it will assign a two weights to that particular word. So it would be 7 and 10, right? The awesome would be 15 and 17, for example, right? Similar type of weights would be assigned to each of the word, and this is done by word embedding. based on the activation function. So activation function, this is, you can consider this as an activation function, right? So the work of the activation function here is it will allow you to cluster your words together, right? So here, awesome and great, those are the words which are related to each other and they can be clustered together. Similarly, pizza is somewhat very different from the great and awesome. It will be into a different cluster, or maybe the individual word that will be a part of that entire model. Moving up to the next layer is the positional encoding. So each of the word is been assigned an unique number, so that in case if you want to so that it doesn't lose the sequence or the context when the output for that particular sentence it needs to be given, right? So that has been maintained using the positional encoding. Next layer to this is self-attention. So the self-attention is each the in this layer, each word is um, find the relevance on to the other word, right? So for example, pizza is awesome. So pizza is been identifying the relation, or you can say the relevance with each other word, like pizza is awesome, right? So is will again check, it will relate to itself and the previous and next one. So is will find the relevance in pizza as well as in awesome. So this is how it works for the self-attention. Let me give another example. John eats pizza and he also drinks Coke. So here, self-attention is going to perform the relevance bar for itself. So John will be compared by itself, as well as it also find a relevance in the next character. Like John likes pizza and he likes Coke. So even a BERT, this model will understand he is the word that is related to John. So it will get replaced as a John there. So this is the work of the self-attention block. The next layer to the self-attention is the sentence is given to the context-aware embedding. So context-aware embedding is similar to the self-attention, the activation function as well as embedding. So the main purpose of the context-aware embedding is to form the clusters of the similar documents. So if there are similar sentences that will be clustered together, like pizza is awesome and pizza is great. In case if there is no sarcasm, if any of the this particular sentence, they will be grouped together, right? So that is how this context aware embedding works. So you can imagine, right, the similar type of words or similar type of documents, not a word, documents are been grouped together. That is the work of the context aware embedding. Next layer is a softmax layer. So this sentence is been given to a softmax layer. The softmax layer is nothing but another neural networks, and it has a responsibility to assign the probabilities for the outcome. So in our case, as we are doing the sentiment analysis, right? So the each of the review has given some probability. If the particular sentence is more towards a positive, it will be given the higher probabilities, right? Whereas it is negative, it will given the lower probability. And based on that, it identifies whether that particular sentence is positive or negative. So this is how the entire encoder architecture works. And we'll see the same thing going forward in the code as well. So this is a link for the code, and you can open the link and can review the code. So in this case, there is an introduction given, and you can just go and read the introduction. It's more similar what I have already discussed in this presentation slide. But yeah, if you want, you can go and read. So what I have done here is that I have installed the transformers, as we are going to use the transformer and the torch. So once the installation has been completed, right, I have been utilized, or you can say use those libraries at Torch. As you can see, I've also used the transformers, which will have the model BERT tokenizer, which we already discussed, and BERT for classes sequence classification. Now, this particular class has been responsible for classifying your data uh, to identify the sentiment analysis, or it can classify the data and create in the groups. And we'll also use AdamW. I'll be discussing this entire classes when I'll be going to actual code for the models. Similarly, we have used a scheduler. Again, I'll be discussing scheduler in detail in our main code. I've used a trend test split to split the data within trend and test that would be required for training the model. I have also used an CUDA, right? This is used for allowing our code to work on the GPU rather than CPU. So this will improve the performance of your code when we use this CUDA as the device. I'm reading the data from this GitHub location. It has a trained data. The data consists of the review as well as the labels, right, which states that whether the label is positive or negative, or the basically review is positive or negative. This will be used to train the model and allow the model to learn from the data set that we are going to provide to it. As we discussed in our architecture, before presenting the data to a model, there are few steps that needs to be followed. The first step is regarding the processing or pre-processing your text, right? The meaning of that is to clean the text and then provide it to the BERT. So we are going to remove all the non-required characters from the text that we want to present. Of course, I'll be keeping the question mark and exclamation because that has a relevance to the reviews. But yes, most of the tags which are not required, I'll be removing it. Similarly, I'll be stripping down the white spaces if they are not required. And this is what I have done for the text pre-processing. Then we go ahead and use the text tokenizer. Of course, that has been required to pass to any the BERT architecture where I'll be using the BERT tokenizer. The BERT tokenizer class itself has a capability of tokenizing a string in a required format by the BERT. So we will be using the same class, and you can see that we are using the model as BERT based uncased here. So this will be performing the tokenization of the strings, or you can say the words, and that will be presented to the BERT model. Moving forward is we will be performing the embedding. So embedding is required for converting your words to a number so that it will be understood by the model at the neural networks to perform the future calculations. So we have written the class sentiment analysis or sentiment data set basically, and we'll be passing the data set and performing the embedding and also adding the paddings to each of the sentence. The BERT requires that each of the sentence should be of same length, right? So we will identify the maximum length of that the sentence in the entire document that we are going to supply to this model, and based on that we'll be creating the or assigning the paddings or the you can say the number as 0 to the rest of the characters or the strings which are not present. That particular padding has been done here. You can see this is the code how it been performed, right? The each of the tokenizer, it will identify the maximum length, and based on the maximum length it will perform the padding to that particular text. So that is also like once we have done this, we define that padding as attention mask, so that the model should be aware about what are the numbers which are actual text and what is the padding that we have been going to perform. So that is the attention mask, and of course will give a model or the model will be provided with details so that the model understand what is the attention mask. Moving down to the preparation of data set. So as you can see, we have cleaned the text here, and then we are going to perform the trends test split, where it will split the data into train and test data set. So here we have using test as a 0.2, that is 20% of data set would be your test and 80% would be train. We have kept the random state as 42 so that at any run, the data is not going to change between the two data sets. It will remain the constant. So once that the Here, once we split the data, we'll pass it to train to a sentiment data set, the class that what we have written on data set to identify or performing the embedding of the data, as well as assigning the padding to it. So most you can see we have passed the trend text as well as 10 test text to that sentiment class, sentiment dataset class, which has been written here. And it will return the input IDs, attention mask, and labels to, to the train datasets and test dataset. And that will be passed as a train loader and test loader so that it would understand or it can be used by a model to consume. So we'll see how the train loader and test loader are being used by the model. So this is the architecture which we already discussed, and I've given you the understanding on this particular architecture. Moving down to the actual code. So as we discussed, we'll be using the main class as BERT for class sequence classification, and we'll be using the BERT base uncased as a model here. And the model is responsible, or the BERT for class sequence classification is responsible for sentiment analysis. It can be used for spam detection or intent classification. We're also using the Adam W here. So the responsibility of Adam W class is to perform the adaptive learning or and as well avoid the weight decay. So the what I mean by avoid the overweight decay is it will avoid the large weights so that it will avoid the overfitting of the model. So overfitting of the model is nothing but the model runs good with all the trend data or the test data, but whenever it's been tested on the actual or the new data, the model doesn't work so fine. So that's the reason we use AdamW, which will allow or avoid the overfitting of the model. We also use the scheduler here. The main task of the scheduler is to reduce the losses. So basically, we have set up the epochs or the iteration. There are 4 iterations that we will be utilizing, and the scheduler decides basically how fast or how slow the model should learn from the data set. So here we are utilizing 4 epoch. So why 4? So I've gone through a multiple iterations and was changing this particular number, but I found the 4 is the optimal number for this particular data set, where I was able to get or gain the expected results, and after that the results remain same. So the 4, that's the number that I have to, but that number can change based on the data that you are going to consume. So once we decide the iterations, I've started training the model here, and you can see we are running the epochs as 4, and I've been utilizing the train loader, what the data set that which we have created in earlier. That data set has input IDs, attention mask, and labels, as you have already seen it. Sorry, yep. As you have already seen it. So the input to this model is your input IDs, attention mask, and labels. So attention mask, as we already described, the attention mask is which allows a model to understand why this particular, what are the meaning of each of the zeros that are being assigned in that particular data set. So it understands where is the data and what is the padding that has been given. So that's the reason we have provided the attention mask to the model. So model will perform its activity. It will identify the loss, right? And each iterations, it will try to reduce the loss and adjust the weight. So the optimizer has the capability of optimizing or adjusting the weights as per requirements. So similar to the train loader, we have written the same code at toast test loader as well. Here as well, we have added the input IDs, attention mask, and labels. It's the same whatever we described in the previous section of train. And we'll be passing the test data to the model to make model learn the accuracy of the model, or you can say how closely the data matches to the trained model. So the code is very similar, which with it will also use the back propagation to make the changes to the weight and reduce the loss while increase the accuracy. And this will be done by the optimizer step. Once this is done, you can view the results, right? At each level of epoch, we are able to see that the losses are getting reduced. So on the step one, you are able to see that it's 3.39, 0.39. On second, it's 0.13. Third is 0.27, and fourth is 0.8, 0.008. So this is how it's been reducing the losses for the train as well as on test as well. We will be able to see how the losses are getting reduced at each and every iteration. We have displayed the precision, recall, F1 score, and support here. This is a table which represents the precision values for the entire model. We have put down the plot to describe how the losses are getting reduced at each iteration. So when we started, it was nearly about 0.25 for the test loss and 0.38 at the train. But at each and every iteration at the level 4, we are able to see it reduce nearly about 0.14 or 13, and as well as for test, it was nearly about 0.02, 0.08 rather than 2, 0.08. As we don't want the model to be trained every time, we save this model using these commands where it saved the trained model, and we can utilize this model for the prediction. So here we want to validate with the new data. Of course, we train the data with whatever the data set we had. Now we want to check whether the data which or the sentences which we are going to pass, whether it's able to identify the sentiment for those sentences. So we'll be loading that model, which we have saved in earlier step, and we will be performing the tokenization, whatever we have done in the previous as well. And we will be passing those sentences to softmax the entire model to, you can see here, to the entire model. And the output of that model will be given to the softmax layer, whatever we've seen in our architecture. So in this case, we have passed this four sentences, which has the movie had a good star cast. This is the worst experience with the movie. Movie is a great, and I had screamed. So these are the four sentences that have been passed, and we can see the sentiments that are coming out. So movie had a good start cast. Of course, it should start, but yeah, the start cast is a positive. This is the worst experience with the movie. That's a negative. Movies are great. That's a positive. I hate the screen is a negative. So this is how we are able to see how the model has been consumed. So to work with this model, I have been working with multiple. You can say I have used multiple references as well as some videos. So I have put down those in my last slide of the presentation. So these are the references. I have used the Hugging Face, Attention All You Need paper, as well as the YouTube videos to go through the details. Of course, I have another links as well that have been used, or you can to understand this entire model. So that's it from my end. Hope you have liked this video, and would really like your feedbacks once this video has been uploaded. Thank you.